So here's a question that pretty much every athlete bumps up against at some point. Can you really be supremely strong and have elite level endurance at the same time? You know, be the total package? Well, today we're going to unpack the fascinating science behind this fundamental trade off.
All right, let's just dive right in by comparing two kinds of modern hybrid athletes. On one hand, you've got your elite CrossFit athletes. These are absolute powerhouses, and the data shows it. Elite males rock a BMI of around 27.1. Now, on a regular doctor's chart, that's technically in the overweight category. But of course, for them, that's not fat. It's just a ton of hard-earned muscle. Then you've got your elite Hyrox athletes, who are built for just insane endurance. They're usually leaner, taller, with an average BMI closer to 24. So why the big difference? This isn't just about what they prefer to do in the gym. It actually points to something way deeper, a fundamental biological limit that seems to force a choice between being huge and powerful and being lean and fast. So what is really going on inside our bodies that creates the ceiling? To figure this out, our first stop is to zoom way in, right down into the muscle itself. Because the trade-off, it turns out, begins with a really simple problem: getting oxygen where it needs to go. And scientists have a pretty cool name for this problem: the size constraint hypothesis. The idea is actually pretty straightforward. See, oxygen gets delivered through these tiny blood vessels called capillaries, which cover the surface of a muscle fiber. From there, that oxygen has to soak its way to the very center of the fiber. And the bigger and thicker that fiber is, well, the longer that journey takes. And here's the crazy part. It all comes down to some really simple geometry. As a muscle fiber gets thicker, its internal volume, that's the part that's screaming for oxygen, grows way, way faster than its outer surface area. And that surface is the only place you can stick those oxygen-delivering capillaries. You just can't add surface area as fast as you add bulk. And that right there, that's the consequence. It creates what you can think of as an oxygen ceiling. A massive, thick muscle fiber just physically can't get as much oxygen as efficiently as a smaller, leaner one. This puts a hard limit on its aerobic capacity, its ability to keep working for a long, long time. In other words, its endurance is capped. But, getting fuel delivered is only one part of the equation. It goes deeper. We also have to look at the very physics of how a muscle contracts in the first place. For the longest time, we thought a muscle's limit was all about total work, basically how much energy it could produce in a single big effort. Then we figured out, okay, it's also about power, which is how fast you can deliver that energy. But now, scientists are realizing there's a third, and maybe even more fundamental limit: a hard-coded speed limit on how fast a muscle can physically shorten itself. So get this. Even if you could somehow give a muscle infinite energy and let it produce infinite power, its performance is still capped. It has a built-in maximum contraction speed that it just cannot break. But where in the world does that speed limit come from? Well, to find the origin of this speed limit, we have to zoom in again. I mean, way, way down to the microscopic level, to the tiny molecular engines that power every single move you make. And this is where things get really cool. Okay, don't let this diagram scare you off. The concept is actually really simple. Inside your muscles, you've got these things called molecular motors, like myosin. And you can think of them as these tiny, tiny little engines that have to climb over a small energy hill to create movement. And they do this millions of times for every single muscle twitch. Now, the secret sauce to how these little engines perform is a specific spot on that energy hill called the transition state. It's basically the tipping point of the climb, the point of no return. And, as you're about to see, where exactly that tipping point is located, well, it changes absolutely everything. So what's the perfect design for these tiny engines? This graph basically gives us the cheat code. It turns out that when that tipping point is really early in the climb, scientists call this a front-loaded design, the motor hits a biological jackpot. It's a total win-win. It produces more power and it's more fuel efficient. This is literally the ideal setup for both strength and endurance. All right, so we've gone from the whole athlete all the way down to these incredible molecular motors. Let's zoom back out and talk about what all this crazy science actually means for your training, for the sweat. Okay, so after hearing about all these limits, the oxygen ceiling, the physics, the molecular engines, you might be sitting there thinking, well, is this just a lost cause? Is it actually impossible to get stronger and boost your endurance at the same time? No, not at all. And the research on this is super clear and frankly really hopeful. There was this one great study that took a bunch of guys who were already seriously into resistance training. They had them add an endurance program for 10 weeks, and the results were amazing. Not only did they not lose any of their hard-earned muscle, but they actually added more capillaries to their muscle fibers, which gave their aerobic capacity a huge boost.
So here's the real takeaway, the bottom line. Yes, okay, an ultimate biological ceiling does exist, but it's way, way up there. It's a ceiling that maybe the top 0.1% of elite athletes ever have to worry about. For pretty much all of the rest of us, there is a ton of room to get better at both strength and endurance at the exact same time. And science even gives us a playbook for how to do it right. The key is to minimize something called the interference effect. That's basically when the biological signals for building strength and the signals for building endurance kind of get mixed up and cancel each other out. The best way to avoid that? Separate your workouts. Try to give yourself at least a 4 to 6 hour gap between a heavy lifting session and a tough run. Even better, if you can, put them on completely separate days. So there you have it. You now know the biological trade-offs from the inside out, from the simple physics of oxygen all the way down to the design of our molecular motors. The only question left is, now that you know the limits, how are you going to train smarter to push your own?